Welcome. In the previous couple of classes, we looked at the very fundamental principles of electrical magnetic aspects, such as Maxwell's equations, charge conservation equation, the electroquasi-state, magnetoquasi-state approximations, the modifications of Maxwell's equations to a biological medium with different permittivity and with different permittivity essentially. Permeability remains the same, as well as the Ohm's law as a constitutive equation in this case. Okay. What we're going to do in this class is look at some very basic relationships that you've known from high school, how they are actually obtained through Maxwell's equations itself. Okay, so they have been derived using Maxwell's equations, but you've been presented that equation so far and you've just been using it as a fundamental equation. The basis for that is all Maxwell's equations. And Maxwell's equations is all common sense, whatever comes out must be equal to what is inside and so on and so forth if you look at it physically. Okay, so it's essentially like material balance. Nothing very different from that. Only thing is the development is in terms of fields and so on and so forth, which is necessary, which is the way the development has happened. And therefore you have that. Okay, fine. Let us start looking at getting useful relationships through Maxwell's equations in this class. Maxwell's equations are a complete description of the electromagnetic phenomena and therefore they are absolutely fundamental. A manipulator of biology, which is you in a couple of years from now, will never fall inadequate while dealing with continuous systems if Maxwell's equations are involved. Of course, continuum is a given. If you have a continuum, especially in biological systems, Maxwell's equations are certainly the fundamental aspect for electrical aspects. However, they are always not easy to use for specific situations. The same way as mass conservation equation, which is essentially mass can neither be created nor destroyed. Okay, that is what mass conservation is. But by the way it is stated, it was not very useful. We modified it to input rate plus generation rate minus output rate minus consumption rate equals accumulation rate, which is essentially saying the same thing. Mass can neither be created nor destroyed. But we write it of the form in terms of the variables that are important to us and so on and so forth, with the time involved, rates involved, time involved, and so on. Then it became very useful to us to apply to processes. Similarly, the Maxwell's equations themselves are directly difficult to, when you try to use them directly, they may not be very tractable. Therefore, special case relations derived from Maxwell's equation, along with constitutive equations such as Ohm's law, that relate current to voltage. Current is charge per time, not charge flux. This is charge per time, charge rate. This is current and voltage, when certain types of materials are considered, are more useful. Okay. So for use, we need to do this. Let us recall what a plasma membrane is. Okay. Plasma membrane is the membrane of the cell, the first membrane of the cell, a lipid bilayer. And depending on the organism, you could have a cell wall and another lipid layer on top of it, 3 layers maximum. Mammalian cells have only a plasma membrane, they do not have a cell wall. Plant cells do have a cell wall. Bacteria have 3 layers and so on and so forth. Okay. So this is the plasma membrane that you could recall from your biology courses, biochemistry and so on, cell biology. A plasma membrane consists of 2 layers of charged lipids, bilayer of lipids, with the charged parts at the extremes and the uncharged parts in the middle. Okay, you know this. Uncharged lipids, lipid parts together. Electrically, a plasma membrane can be viewed as a system consisting of charges at the surfaces that are separated by an uncharged or a dielectric material, lipids. Okay. So you have a lipid and a head group, you have another lipid and the head group, lipid parts come together, the head groups charged are separate. So you have charges separated by this dielectric lipid. Okay, that's one of the ways of looking at it. The dielectric lipid is in between the charges. Does it remind you of some electrical device? basic electrical device. That's a classic capacitor, isn't it? You have charges separated by a dielectric, charge plates separated by a dielectric. It's nothing but your classic capacitor. And we'll use Maxwell's relations to derive the basic capacitor relationship, and thus you could see how the plasma membrane can be considered as a capacitor. To begin with, let us consider a flat surface area A. Here, this is a flat surface. I've just drawn a section of it, therefore it looks like a rectangle. It has another dimension into the screen here. Flat surface of area A of uniform charge density rho, okay, net charge density is rho, and uniform surface charge density as rho dash. Okay, surface charge density is density per unit mass, sorry, density per unit area. In this case, surface charge density, therefore rho dash is density per unit area. Note the charges are on both sides of the plate here. And you know the electric fields, how to draw the electric fields. They're drawn from the positive to the negative, and in this case, they're all straight lines emanating out of the plate. And we're going to consider this as a system for analysis. So let us consider the rectangular or cuboidal control volume around it as a system. The charge contained in the control volume is nothing but rho dash, which is the surface charge density, times the total area, because charge by the area is your surface charge density. Therefore, the total charge is surface charge density times the area. In this case, each area is A, and therefore the total area is 2A, and rho dash times 2A, because there are two surfaces, each of area A, would be the charge contained in the control volume. The electric field strength is E. The arrows indicate the direction of the electric flux from the positive to the negative. To draw the electric flux lines, the following principle is used. This is to recall from your high school. Electric flux line always starts in a positive charge and ends in a negative charge. Okay, so this is the electric flux lines that are drawn for visualization. If the charge is a point charge, the following would be the flux lines. If the point charge, then it emanates in all directions from the positive charge here, and these are the flux lines. Okay, this is just to tell you or to review how to draw flux lines. This is the electric field due to the point charge here. Now, we are going to consider one plate of a typical capacitor, which is this. The capacitor has two plates. Okay, so there are positive charges on one side of the plate alone here in this capacitor. For the system shown, let us write the Gauss's law, which is Maxwell's equation. Gauss's law is nothing but surface integral of E dot dA equals Q, the charge, divided by epsilon naught. Right? This you know as Gauss's law. Go back and check the form, then come back and see whether this is fine. So E is nothing but rho dash of A divided by epsilon naught. This is the surface charge density. Surface charge density times the area would give you the total charge divided by epsilon naught. This is the surface charge density. So you have it per unit area. This is at every single area you have this flux, and this varying with the various delta A's that are there, and this is the integral form, this is the differential form. Now, let us look at the total capacitor with the two separate charge surfaces. Since there are two surfaces each of area A, E times 2A equals rho dash times 2A divided by epsilon naught, or rho dash by epsilon naught, which is E times 2A. Okay. So, you are considering this as well as this because you have two plates here. This is the equation 5.5.1-1. Thus, epsilon is nothing, E is nothing but rho dash by epsilon. We are cancelling the two A's on both sides of this equation that we got from Gauss's law. Note that we got this relationship from the very basic Gauss's law, and now we are going forward with this. So you cancel 2a on both sides, you get E equals rho dash by epsilon naught, equation 5.5.1 dash 2. The integral of the electric field with respect to the displacement gives the potential difference, that you know, right? The E equals del of V, and therefore integral of the electric field with respect to the displacement gives the potential difference, delta V. Okay, you're going to integrate that. Therefore, delta V is nothing but E dot dl, equation 5.5.1 dash 3. So if you need to understand this, go to the definition of electric potential in terms of the electric field, then you'd understand why del V is E dot dl. If you integrate this, we get del V equals, what is E dot dl? E is rho dash by epsilon times the integral of dl is d. So this is what it is, 5.5.1 dash 4. Does this remind you of something? D is the distance between the capacitor plates, and rho dash is the surface charge density, or Q by A, and therefore that equation can be written as delta V equals QD by A epsilon naught, or this is 5.5.1 dash 5. The capacitance, which is defined as charge per unit potential difference, this is the definition of capacitance. Recall the definition of capacitance as charge per unit potential difference, charge per delta V, is nothing but A epsilon naught by D. Okay. This is the capacitance of a parallel plate capacitor that you have seen from high school days. Okay. And this we have derived using Gauss's first, Maxwell's first equation, Gauss's law, Maxwell's first equation. So fundamental equation applied to the capacitance case gives you this, and this can be extended to the lipid bilayer membrane of a cell. Okay, capacitance, because it can be viewed as charges separated by a dielectric material. This is equation 5.5.1 dash 6. Okay, so we have seen how you could use a fundamental equation, the Maxwell's first equation, to derive the capacitor equation. Now I'm going to make a big jump. Okay, especially electrical engineers would feel very rattled when I do this. Don't worry about it. I'm just going to, my purpose is not to make you expert electrical engineers, experts at use of Maxwell's equations and all that. That's not the purpose here. This is just to tell you what all are relevant. And then at a later stage, whenever you need it, you can go pick up the necessary additional skills to become experts in this. Okay. So I'm going to jump now significantly. I'm going to talk about something called EEG. Okay. I'm sure you would have heard the term EEG, electroencephalogram. Okay. This is, of course, a medical tool, electroencephalogram. The nature of EEG gives an idea of the brain activity. This you all know. For example, if you are normal awake, then the EEG would look something like this. Okay, this is the time scale. This is 0 to 3 seconds. Okay, you will have a lot of squiggles in your EEG if you are awake. And if you are in deep sleep, if you look at the scale, it is 0 to 100 microvolts. It goes through a nice rhythmic pattern in deep sleep. And when you're brain dead, it's flat. Okay, there's no electrical activity when one is brain dead, and therefore that is flat. So EEG gives you an idea of what this is. This is a very useful tool in medicine. We all know this. And the basis for design of EEG is the Maxwell's equations. Okay, are the Maxwell's equations. EEG is obtained by recording the voltage on the skull surface. Okay, you have all those leads that go out and measure. The currents that are generated in the brain cause the voltage, which are measured. And simplistically speaking, again, very simplistically speaking, we can consider the brain to be a charge of a certain density enclosed in a volume, which is the skull. Okay, so you could look at it that way, some charge that is enclosed in a skull. can be considered as a non-homogeneous, changing in all directions, of course, finite volume of charges. Okay, so that brain, of course, is non-homogeneous. You cannot have the same thing all over the brain. Then the brain, there's no point in having a brain. So this is a non-homogeneous finite volume of charges. Starting from the Maxwell's equations, it can be shown. This is a nice book, Malvivo at Ploncy, 1995. Please, if you're interested, go read the book. It's a reference book for us, that is, it's a textbook for electrical engineers. That for a non-homogeneous finite volume conductor, this relationship is valid. Okay, 4 pi Ke times the potential equals integral over the volume I dash dot del of 1 by r dV plus epsilon of plus summation over j of the surface integral Ke2j minus Ke1j v del of 1 by r dot ds. Okay, so if you want the derivation of this, go to this book. It has been given, at least the key steps are given in that book. So they start from the Maxwell's equations and get here, or you need to start from the Maxwell's equations. That's a bedrock, bottom line, and then you can build this up. And such a useful device as the EEG is based on Maxwell's equations. Here in this equation, Ke2 and Ke1 are the conductances at limiting differential surfaces of the inhomogeneous conductor divided into differential sections. Don't worry too much about this. I needed to define this. I mean, this cannot give you a Ke2 and a Ke1 without mentioning what they are. It doesn't really matter to us. The main idea is for you to appreciate that Maxwell's equations can lead to very, very useful relationships. Key equation for EEG is derived from Maxwell's equations. This is the key equation for EEG. Okay, that is what I have in this class. We'll meet in the next class and take things forward. See you then.